Okay, so let's take a look at the electrolysis of water, and I'll actually demonstrate this in class. But if you put water into an electrolytic cell and apply electricity, you'll get oxygen gas and hydrogen gas. And one of the nice things is you'll see that there's twice the volume of hydrogen gas as there is in oxygen gas. And actually, an experiment like this was what led scientists to understand that water was actually 2 parts hydrogen to 1 part oxygen. So anyways, if we look at what's going on in the cell, at the anode, that is the positive ion where oxidation takes place. The cathode is the negative ion where the reduction takes place. So if you look at the two reactions that are on your standard reduction potential, here we have water going from, so in the oxygen case, it's going from a -2 to a 0. So that's going to be an oxidation. And so when I flip it, I get a minus 1.23 volts. If I look at what's happening on the, what's going on with water, the reduction reaction actually has the hydrogen going from a +1 to a 0. So that is a reduction. And if I balance the equation, the overall equation ends up becoming simply water becomes hydrogen and oxygen. And the voltage required to separate those two is 2.06 volts. Okay, so let's take a look at the other common use of electroplating. So let's say I have this spoon that is, let's say it's made of steel, and I'm worried about it getting rusted, so I want to coat it with some silver. So I can electroplate the silver onto that spoon. So what I have to think about is which electrode is going to be the plating metal and which electrode is going to be the object to be plated. So I show here that the spoon is on the cathode, but let's take a look at why that is. So on the cathode, so if I look at what I want to do, I want to produce, I have silver metal in solution and I want to produce silver. So I'm going to start with Ag plus 1, add an electron to it, and get silver. So this is going from +1 to 0. So this is a reduction reaction, which tells me, because reduction happens at the cathode, red cat, right? This silver must be the anode. Okay, so if you're asked to figure this out, that's how you would do it. Is you look at, you want to create the metal, that's going to create a reduction reaction, and that will happen at the cathode. So if you think about what's happening, if this is my anode, this is the positive side, electrons are going to float this way, right? And so I have my spoon, the electrons are going to leave the silver, positive silver is going to go into solution, it's going to dissolve, right? And on this side, I now have a cathode that's negative, so the silver ions are going to pick up this electron and they're going to become silver metal, and that silver metal over time is going to coat that spoon. You can do the same thing with a key or any object. Okay, so that's how electroplating works. And of course I need a battery, right? This is not a galvanic cell, this is an electrolytic cell or electrolysis. Okay, so we can look at electroplating problems. Those are the most common mathematical problems that you'll have on the electrochem part of the test. So there are typically two types of problems. One asks how much metal can be plated out, and the other will ask how long it will take to plate things out. So you need to understand what all of the terms mean. So 1 volt, you got to remember, is 1 joule per coulomb. 1 amp, a new term, is the number of coulombs that can be passed per second. And this has a abbreviation of I. Strange, there's no I in the word amp, but I, or what people call inductance, is equal to 1 coulomb per 1 second. And then there is this thing called Faraday, and a Faraday is 96,485 coulombs per mole of electrons. So we often talk about this as Faraday's law. And the Faraday's law is simply that 96,485 coulombs are 1 mole of electrons. Okay, so let's take a look at how we would apply this. But first of all, if you look on the equation sheet under the heading of electrochemistry, you see all of the equations for delta G equal, including the negative nth equation, negative NFE. Okay, you also see I equals Q over T. Now Q here is listed as coulombs. That's also what we're calling C. And T is time in seconds, so C over S, coulombs per second. Okay, and that a coulomb per second is an amp, and it's got an abbreviation of I. Okay, so all of this information is here, and you just need to remember to use it. And I like using coulombs per second for an amp instead of Q over T because it makes the stoichiometry and canceling out units a little more straightforward. So doing these type of problems is very much dimensional analysis. So we want to know how long must a current of 5 amps. So 5 amps means 5.00 coulombs per 1 second. Must be applied to a solution of silver plus to produce 10.5 grams of silver metal. Okay. Okay, so when we're doing factor label, we're always trying to figure out what to start with. So if I have a derived unit, which is one unit over another, that's usually not a good one to start with. So I'm going to start with my 10.5 grams. So I have 10.5 grams of silver. And what I know is silver's molar mass is 107.87 grams of silver, is 1 mole of silver. Now I have to get to moles of electrons so that I can use Faraday's number. So what I know is 1 mole of silver will exchange 1 mole of silver electrons. Okay? And for every 1 mole of electrons, it's 96,485 coulombs. And what I know based on this 5 amps is there are 5 coulombs per 1 second. So if I multiply all this out, I can cancel everything. It cancels really nicely. I end up with 1,878 seconds. And if I divide that by 60 seconds per minute, I get 31.3 minutes. Okay. So go ahead and try this one on your own. Here I have calculate number of grams of aluminum produced in 1 hour by 10 amps. So 10 amps is 10 coulombs per 1 second. So I'm going to start with 1 hour. And 1 hour is 60 minutes. And 1 minute is 60 seconds. And now I can use this. 1 second is 10 coulombs, and 485 coulombs is 1 second. I mean, it's 1 mole of electrons, and there are 3 moles of electrons in 1 mole of aluminum, and 1 mole of aluminum is, let me see, 26.98 grams. So if I multiply all that out, I get 3.36 grams of aluminum. Alright, let's do one more, or 2 more. Alright, in the electroplating of copper, half a Faraday of electrical charge is passed through a solution of copper sulfate. So what mass of copper is deposited? Alright, so I have a half of a Faraday. And what I know is 1 Faraday is 96,485 coulombs. That's the only conversion I know for Faraday. Now I can use that same conversion, 96,485 Faraday, or 1 coulomb. Let's back that up. 96.485 coulombs is 1 mole of electrons. And this is copper plus 2, so 2 moles of electron is used for 1 mole of copper, and 1 mole of copper is 63.55 grams of copper. And if I multiply all that out, cancel all my units, I get 15.9 grams of copper. One more. All right, how many seconds will it take to plate out 5 grams of silver from a solution of silver nitrate? That's 20 amps current. So that's 20.0, and this is going to be coulombs per second. Okay, so I'm going to start with my 5 grams of silver. What I know is 107.87 grams of silver is 1 mole of silver, and 1 mole of silver has 1 mole of electrons, and 1 mole of electrons is 96.485 coulombs, and 20.0 coulombs is 1 second. And if I multiply that all out, I get 223 seconds. Okay, we're going to stop right there.